Okay, so that was about the valence, right? And again, the bonds, they called covalent bonds. And as I said, they're very, very strong bonds. And as I said, there's another thing. Another thing is a charge, as I mentioned. So when atoms lose or gain electrons, the charge on their atom changes, right? And this charge also has a quite strong ability to pull, right? So you can see electronegativity is atoms' attraction for electrons in covalent bond, right? So having like spots available, right? It's gonna pull on it, like it's gonna pull electrons, attract them. And there's something called polar versus non-polar bond. And it's plays quite serious role whether a molecule was called polar or non-polar. And let me show you this. I need a whiteboard. So when you see, for example, when you see H2, right? 2 hydrogens. So you can see 2 hydrogen atoms, right, combined together, sharing 2 electrons, right here. So the charge between these 2 hydrogens is evenly distributed, pretty much, right? These 2 electrons move around them. So this is what's called non-polar molecule. When you look at H2O, right? So this is a very large oxygen, right? This is the oxygen atom. And the thing is that where it makes bonds with hydrogen, right? Oxygen pulls, it's a large atom, it pulls electrons from hydrogen, pulls them away, leaving hydrogen positive, right? And making other side of the molecule more negative. So it's pretty much like a magnet, really. It's like a magnet that has at one end positive, negative charge, and another end it has positive. So this is called polar molecule. Polar molecule means it has, let's say, one side negative and another side positive. Polar molecules, like magnets, they really tend to stick to each other. And that's basically what creates connections between the molecules, not within the molecule, not the bonds within the molecule, but the bonds between the molecules. It really matters if the molecule itself has either even distribution of charges or uneven distribution of charges. Is it clear, guys? No, tell me, is it clear? So this is, this symbol indicates a charge, right? So you can see large oxygen, right? 2 tiny hydrogens, and oxygen really pulls electrons to itself, making this end of the molecule charged negatively, and this 2 hydrogen charged positively. Okay, and that's what I just showed you. Hydrogen is non-polar molecule, right? While water is, it is. And this is about ionic bonds. So it's about positively charged ions, cations, negatively charged anions. And that's what called, this is something about ionic bonds. Ionic bonds is when, for example, sodium loses electron, right? Sodium becomes positively charged. Chlorine picks up electron, becomes negatively charged. They don't really share electron, but rather attracted by charges. positive charge, negative charge, right? This is ionic bond within their molecule. By the way, it's a molecule called salt, right? Not just because it's a table salt, but just, you know, metal with their non-metal. This is a salt, okay? And this is a video basically of formation. I don't know. Let me just check what is. Can you hear it? Guys, can you hear if I play this video?
No.
No. Okay, so that's why I don't play them. Okay, and as I said, ionic compounds or salts, right? And what you can see, salts usually very stable when they dry, like a table salt, but they mix well with the water, and you're actually gonna see in the next part why they so easily get mixed with the water. Again, the charges on the molecule, charges on the ions play a huge role. I think more important role than you know, just elements. So that's how these bonds actually are formed, right? This is a crystal, right, of the table salt. And what you can see, positive, negative, right? Positive, negative, positive, negative. They're quite stable in the attraction. And there's something called weak chemical interactions. What are weak chemical interactions? I mean, they might be weak separately, but they could be quite strong if, you know, they're quite strong when they are, there are many of them. And a very important type of bond is the hydrogen bond. Let me show you what is the hydrogen bond, and then you'll take a break, actually. Hydrogen bond is, again, water, right? Water molecule. Hydrogen is positive. This is ammonia, right? NH3. So nitrogen and 3 hydrogens. Ammonia is also a polar molecule. Hydrogen bonds can be formed only by polar molecules because, you see, positive charge, negative charge. They're not ions, these are molecules, right? But molecules with, again, distributed charges. So positive and negative. You can see it's the same thing in water molecule itself. Again, the same hydrogen bond. So this is oxygen, right, negative. Hydrogen, that is positive. Hydrogen, that is positive, right? So another hydrogen, that is positive. And oxygen, that is negative. Another hydrogen, that is positive. This is the same hydrogen bond. When hydrogen, right, that has a positive charge, is actually attracted to the negative charge on atom of another molecule. That's how hydrogen bonds are formed. Okay, hydrogen bonds you're gonna see are super important keeping 2 strands of DNA molecule together. When we get to DNA, I'll definitely show you again how hydrogen bond is relevant in this molecule, okay? So one more time, a very important bond between positively charged hydrogen and negatively charged atom on another molecule.
I have a question.
Please, finally question. Yes.
In the diagram that you just drew, I noticed that one hydrogen was sharing with 2 oxygens.
Okay, let me go to that one.
On the whiteboard.
Yes, so basically, yeah. So this is hydrogen on one molecule, right? But it's kind of like sticks to negatively charged oxygen on another one. So you see minus and plus, right? Minus on the oxygen and plus on the hydrogen. That's what keeps them together. these two hydrogens here, this one and this one, right? They're part of the molecule. But this hydrogen is a part of another molecule, right? But it sticks to negatively charged oxygen. It's like, you see, if you take magnets, right? Plus and minus, you put them together, what's gonna happen?
They're gonna attract.
Exactly. So this is the same thing. Think about these molecules as magnets, right? With positive and negative sides. And when you put many of them together, they tend to stick. And by the way, if you have a bunch of magnets, right, that stuck together, is it easy to break them apart? Is it?
No, because
No, it takes some effort, right? That's basically the same thing in chemistry. When you want to break this type of bonds, you have to provide energy. So for example, molecules in water, if you take like, you know, this is a liquid, right? This is a water, which is a liquid. So they are held by hydrogen bonds, right? To break down these bonds, what do you have to do?
heat it.
You know, exactly, awesome. You heat it. So which means the energy from the heat will be used to break them apart. Okay, like if you have magnets, again, as I said, you have to make an effort. Okay, guys, it's 9:20, so I'll see you in 10 minutes. Okay, let's take a break. So 9:30. This is not the one. This is called van der Waals interactions. So van der Waals interactions is actually, if you talk about the polar molecule, right, with distribution of charges is not the same, distribution of electrons, right? Sometimes they tend to accumulate in one part of the molecule. And what happens that if you have in one part of the molecule, you have positive charges, and another part of the molecule, you have negative charges. And you have many, many molecules like that, many, right? So in this case, together, these interactions can be quite strong. And example of this van der Waals interactions, again, they're very, very common. Like I think very good example of van der Waals interaction, just imagine plastic bag, right? Like a plastic bag in the supermarket that you try to open. Yes, guys, you know what I'm talking about?
Yes.
Or like a surface, again, the surface of, again, plastic that sticks to something. This is van der Waals interaction, exactly. You have a bunch of molecules, right? And there are charges accumulated on the surface of these molecules, and these charges can actually interact with other molecules on another surface, right? Like gecko, right? Gecko, you don't say gecko, you say gecko, right? You see this tiny hair on the toes, right? So these tiny hairs actually have a charge on them, right? It could be positive in one place, negative in another place, but these charges are accumulated on the surface. And that helps gecko to stick to the walls, right? Because believe it or not, walls might also have some charges. Maybe tiny, but they do exist. As I said, you can hardly find anything that is completely neutral, right? Even again, non-living matter might accumulate charges, like charges when, for example, on the doorknob, right? When you touch it and you get a, you know, I think that's actually
Get shocked.
yes, you get shocked. I think a really good example of van der Waals interactions. It's not like a static electricity, but still, it's like static electricity also like definitely contributes a lot. but I should say, like, no, it's actually a bad example. No, I think plastic bags in the grocery store are probably a very good example of van der Waals interaction. Okay, anyways, and the shape and function. So molecules, they do have shapes, and shapes actually determined by their orbits of electrons. So remember, I told you some orbits are spherical, but some orbits look like petals, right? Water molecule actually looks, some say that it looks like upside down Mickey Mouse, right? Yes. Because what you can see, hydrogen kind of accumulated, like two hydrogens, they are not evenly distributed, right? They are on one side of the molecule. And this is due to the ways actually electrons travel in their shells, right? Methane is like, it looks like a pyramid, right? Methane, by the way, is not a polar one. Methane is a non-polar molecule. And the shape of molecule actually is a very important thing. What's a very important thing? Because from how these molecules interact with each other, and specifically how these molecules interact with cells. The thing is that in living organisms, molecules, and you know, some molecules could be quite simple, for example, nitrogen oxide, like NO. NO is a very simple molecule, but NO is a chemical messenger. And this is a molecule that actually helps to relax walls in the blood vessels, increasing blood flow in these blood vessels. Okay, some molecules are much more complex, but to signal, I mean, to interact with a cell, they have to bind to something called receptor. It's like a sensor. This receptor is usually found on the wall of the cellular membrane, right? It's like an outer wall of the cell. This is the cell membrane. So this is receptor. This molecule is an endorphin. It's a molecule released by part of the brain called hypothalamus pituitary in response to stress, in response to, you know, feeling high from exercising, you know, from like some physical activities. This is a molecule produced by human body, right? This is receptor that this molecule signal. This is a morphin that is not produced by the human body. But what you can see, this part of the molecule of morphin, very pretty much similar, identical to the key part of endorphin. So morphin can bind to the same endorphin receptors and exert its effect. Morphin is a painkiller like endorphin. Morphin is can make you sleepy. Morphin can make you feel relaxed, right? The only problem is that morphin concentration is usually far, far higher than concentration of endorphins released by the brain. And that's what can make a difference, and that's what can cause addiction, okay? So that's pretty much how drugs work. Drugs resemble natural molecules released by the organism, and structurally being similar, they can exert the same effect over the receptors. Okay, guys, make sense? Yes? Hello, are you with me?
Yes.
Yes.
Awesome. Okay, so the last part from here is about chemical reactions. So chemical reactions happen when the bonds between their elements in the molecule and the compounds are broken, right? And you start with their molecules. Could be 2, could be 1, could be more, right? But you start with the reactants. And by the end of the chemical reaction, you get products, okay? Chemical reactions, we're gonna talk more about them, but they could be quite different in terms of how much energy they need to consume in order to run, or sometimes they can release chemical energy during the chemical reaction. We'll talk about this, I think, like probably in a week or 2. Doesn't matter. Right now, let's see. 2 hydrogens, 2 hydrogen molecules, plus 1 molecule of oxygen. It actually takes quite energy to produce 2 molecules of water, right? So one more time, you take 2 molecules of hydrogen, 1 molecule of oxygen, and you get 2 H2Os. If you just mix them together, nothing gonna happen. You really have to give like a shot of energy for this reaction to happen. Another chemical reaction that is quite important is reaction of photosynthesis. Photosynthesis conducted by plants, right? So plants take 6 molecules of carbon dioxide, 6 molecules of water, produce 1 molecule of glucose, and 6 molecules of oxygen, okay? Now, some reactions can go both ways. So, and as I said, some reactions consume energy, some reactions release energy. So for photosynthesis reaction, the energy comes from the sunlight, right? So sunlight is the one that actually makes this happen. And if you watch photosynthesis actually in the water, you put the leaves in the water, you can see these bubbles of oxygen released actually during this process. This is a very nice experiment that usually done in the lab for bio 210, yeah, but not in these days, unfortunately. And as I said, chemical reactions reversible, not all of them, actually not, sorry, not all of them. So you can see arrows going 2 ways. So this is hydrogen and nitrogen and gives you 2 molecules of ammonia, right? But it can go 2 ways. And chemical equilibrium is actually happens once there is a balance in reactions that can be reversible, right? When the balance is reached, like how to say, half of them will be reactants, half of them will be products, okay? That's when the balance is reached. Okay, guys, this is chapter 2, right? Unfinished chapter 2. Chapter 3 is quite short, so it probably will take us like half an hour to complete. Any questions? For how many of you this material is completely new? Awesome. That's great. Because for those that like, again, I believe if you see this material for the first time, it can be a bit intimidating, but I'm glad that it's not the case. So one more time, any questions on this chapter? Okay, okay, fine with me. So chapter 3, Chapter 3, I really like this chapter, and this is the chapter. I'll try to show you a video. I mean, you can watch the video without sound, it's still cool. I can actually be the sound. Okay, so chapter 3 is about water and life. Okay, and this is an ACO. I don't know what seal is doing here, but it's doing probably something. There is something here. Okay, how does water surface allow its solid form ice to float on liquid water? We're gonna talk about this. And liquid water molecules can sleep closer together. In ice, water molecules are much further apart, right? So that's why ice floats, because the density of ice, what you can see here, is actually lower than density of liquid. Okay, water is unique substance. Why it's unique substance? Because this is the only substance that can be easily, easily go from liquid to solid to vapor. It, like we say, it's easily, right? Because we see it in front of us. We're gonna see actually that it's not such an easy process. This is the process that takes quite a lot of energy, right? But it's pretty much due to their fact that I explained to you that water is a polar molecule. Being a polar molecule, having uneven distribution of charges is actually what contributes to unique properties of water. That's probably a reason why life is impossible without water. Why life started in the water, and why water actually still takes more of their, takes more space on Earth than land, right? You agree with me? So polar covalent bonds, right, within the molecule of water. But between the water molecules, as you can see, it's a hydrogen bond. Hydrogen bond is considered a weak bond. But being a weak bond, as you're going to see, it still takes an effort to put these molecules apart, right? So again, like magnets, these molecules stick to each other. And because they stick to each other, they create something called cohesion. Cohesion is basically sticking to each other, sticking to the surfaces. And this cohesion creates surface tension, right? So surface tension one more time, because they stick to each other. And due to the surface tension, things can do many things, right? So insects, a bunch of insects can run on the water. Things float, right, on the water. Probably also reason why water can support your body, right? When you swim. Guys, you follow? Are you with me?
Yes.
Yes. Okay, so I want to show you something. As I said, I hope it's gonna work. The sound. I'm gonna make it the loudest, but if it's not gonna, will be this. Have you ever seen this video before?
What do you think a private Christian education looks like? GCU offers over 175 high-quality online programs. Find your purpose at Grand Canyon University. Visit gcu.edu.
Some young Costa Rican basilisk lizards are looking for food.
It's a Costa Rican basilisk lizard looking for food.
Jesus Christ lizard.
We can hear
Jesus Christ
This adult
lizard.
male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the
This is a
territorial
female.
male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries.
Oops, sorry. So, can you hear, guys? Can you hear the sound or not?
yes.
Yes.
Okay, awesome.
This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, it can run on water. It bicycles its hind legs, and the tail becomes a counterweight. We can't know what the snake is thinking. Did it really want to eat the lizard, or did it just want to show?
Okay, I really like this video because it's actually, yeah, I think this lizard definitely is a champion in running on the water. Although again, there are plenty of insects that can do the same, but I think this is the only reptile that can do so. But as I said, surface tension, one more time, is pretty much due to the hydrogen bonds. And due to cohesion, right, due to the stickiness, and also if you create some pressure, this is probably the reason, it's not probably, sorry, this is the reason why water moves up their plants and even the tallest trees, right? So the evaporation, right, and evaporation means when the bonds are broken, right, and molecules become separate from each other, right, but there's still they tend to stick to each other, right? And that's again, I think is a very good example why it's so important. And moderation of temperature by water. So this is a quite interesting subject of how water, what role water plays in moderation of temperature. We talked about potential energy, like energy that is locked. As I said, it can be locked within the battery. Well, potential energy is when you have like a ball on the top of the shelf, right? So this is the energy locked in the ball once ball gonna drop, right? Kinetic energy is an energy of motion. This energy of motion, I think good example could be the windmill, right? So water moves the mill and the mill can do the work. But one form of kinetic energy is thermal energy. Okay, so thermal energy is related to definitely to temperature, and it's pretty much how molecules move, right? You increase the temperature, you give them the boost for the movement. And when thermal energy moves from one body of matter to another body of matter, it's defined as heat, right? So it's also related to calories, right? I'm sure you heard about calories. So calorie is amount of heat which is required to raise temperature of 1 gram of water by 1 degree Celsius. This is definition of a calorie, right? I'm pretty sure that you understand that calories that we consume, right, they could be used for different reasons, but one of them is to maintain our body temperature, right? Also, when we move, our muscles generate heat as well. And that's how I say we burn calories through movement. And this is about like food packages. When you see calories, you usually see like a bunch of them, like kilocalories. Another unit of energy is joule, but I think we're gonna stick to calories in this course. So water, like, you know, it's not really about water, but there's something called specific heat. So specific heat is actually how much heat the substance has to take in order to bring the temperature up by 1 Celsius, right? For 1 gram of the substance. So specific heat could be referred not only to water, it could be referred, as I said, to anything. Now, water, specific heat is 1 calorie per gram for 1 Celsius, 1 degree of Celsius. And believe it or not, it's actually quite high. Alcohol, for example, is 0.6. I think acetone is even lower. Think about it, like if you want to heat water, right? So you put water in the pot on the stove. It doesn't begin to boil instantly, right? It takes a while to boil. Yeah, you agree with me? If you ever try to do the same with the acetone, you'll be surprised how fast acetone gonna boil. Another thing is that, have you ever like get like a burn from the vapor? Did you ever burn yourself with vapor?
Yeah.
Yeah, it hurts, right? It's super hot. So basically, this specific heat of water indicates that it's not that easy to bring the water temperature up. It's not also easy to bring it down. So you see, water resists changing its temperature, and it's great. Just imagine for a second, if the specific heat of water will go down to that of alcohol. My goodness, I think we'll die from humidity, right? Imagine how much water will be in the air then. Yes? Yes, guys?
Yes.
That's why, for example, water in their lakes, in rivers, in ocean is relatively stable in terms of temperature because of the specific heat. And for example, in a like hot day, in a really hot day, you get into the water and it might be surprisingly chilly. Yes. Yeah. I mean, like think about it. Usually, if you go like, for example, to the beach, right? Maybe not this year, but let's say at the beginning of the season, water will be cold, right? Maybe by the end of the season, water will be much warmer. Who can tell me why by the end of the season, water will get warmer than at the beginning? If let's say the temperature is the same. Who can tell me that? What makes a difference actually? What makes a difference, let me tell you, it's not temperature during the day. Let's see, during the day, temperature could be quite high, right?
Is it the change in the hydrogen bonds?
It's about temperature during the night, right? If night is chilly, then the water in the morning will be chilly. Yes? If temperature is the same during the day and night, it's pretty high, then the temperature of the water in the morning will be also high. Okay? So the thing is that water heats the air. Okay, so if air goes down at the night, the water in the ocean will give off the heat to bring the air temperature up. When the water gives off the heat, its own temperature goes down. Okay, so if you want warm water, it's like in the tropical countries, right? The water is relatively warm, yes, during the season, and it's again due to the temperature, it doesn't really change much between the day and night. But if it changes, then you're going to see the difference. Okay, so let's go back to this. So this is specific heat. Now, specific heat is related to hydrogen bonding. Heat is absorbed when hydrogen bonds break. Interesting, right? Heat is released when hydrogen bonds form. What does it mean? Heat is absorbed when water evaporates. Yes? Yes? Heat is released when water undergoes what? When water turns into, basically when vapor turns into water. Okay? So you see what's interesting? Absorbed when bonds break, released when bonds form. Please pay attention to this one. Okay, and and that's what I was talking about. The large body of water can store huge amount of heat from the sun during the daytime, right? And it can warm up only a few degrees. And that's why also, for example, pretty much due to the same idea, when water freezes on the surface, right, it's still liquid underneath. So there are plants and animals that live in the water can survive, right, during the winter. Yes, makes sense? Fish can still survive and swim even if there's a layer of ice. Why? Because again, water resists change the temperature. So even if you have a layer of ice on the surface, it still doesn't go all the way down in, again, in lakes and rivers. And this is pretty much, let's say, I don't know what it actually indicates. This is California, and it shows that, yes, water, right? Next to the coast, you see temperatures are usually lower than away from the water because the water can help to cool the air down. And evaporation, right, is when water is transformed from liquid to gas. And to vaporize, to break the bond, right? Remember, to break the bond, heat has to be absorbed, right? And when water evaporates, it actually cools the surface because it takes the heat energy away. And let me just show you this. Oh my God, I think I left my pen upstairs. Okay, let me draw it down. Okay, so this is skin, right? You agree with me? This is the skin? Okay, so this is, oh my gosh, I can't draw this. This is a sweat gland. They look like hoses, right? So when the body temperature goes up, right? And the body temperature normally, you know, what's the body temperature? Normal body temperature is, I think I told you, is from 98 to 99, right? But when your temperature goes up, what happens to you?
You sweat?
You sweat. So what does it mean, sweat? It means that blood rushes to your skin surface, right? And your sweat glands get activated, and sweat is released on your skin, right? What is sweat? Sweat is water, mostly water, plus some chemicals. So next thing that's gonna happen to the sweat, it's gonna start evaporate from your skin surface. Now remember, evaporation is when the bonds broken. And when the hydrogen bonds are broken, what they do, they take away the heat energy. So you cool down by sweating. You might not realize it, but you do cool down when you sweat. What's the most important thing for you to cool down? The most important thing is that your skin surface will be exposed to air, right? If you will be sweating in a jacket, what can happen to you?
You can pass out.
Yeah, absolutely. Yes, because, you know, so that's why normally when it's hot, what do? We take off the jacket, right? We take off the jacket. So to allow air move around your skin and help to, you know, help with evaporation, right? That's why if you sweaty and you step outside and it's wind, what are you gonna feel?
Cold.
Yeah, absolutely gonna feel chills. Why? Because the air moves around your body. So, which basically opposite is true. If it's cold, right, you put on a jacket. You put on the jacket to prevent this heat loss, right? Makes sense how water actually plays, what role water plays in controlling your body temperature. It's super, I mean, that's why dehydration could be quite dangerous thing. So this is evaporative cooling. And this is, you see, Or like elephant, right? Like since you know that not too many animals are actually able to sweat. Humans can sweat. What do you think? What animals also able to sweat? Elephants can't. That's why they put water, right? Water evaporates and takes the heat off. But can you tell me what is a sweaty animal that you know? Hmm? Leonardo, can you think about sweaty animal?
Not sure. Dogs, maybe?
Have you ever seen dogs sweating?
Monkeys,
No.
apes.
No, apes don't sweat. Mm-mm. Dogs actually regulate the body temperature. The water evaporates from what? Exactly. Yes, dogs sweat through the mouth. Absolutely. Okay, two animals that I can tell that sweat. Horses. Horses sweat. And you know who also sweats? Hippos. But their sweat is what color? Hippo sweat is red. I don't know why. I don't have an answer why hippo sweat is red. But no, monkeys don't sweat. Monkeys have fur. Basically, all animals that have fur, they don't sweat. They don't have sweat glands in the fur. Horses have fur, but I don't know why they still can sweat. But they do. And many animals, remember, I think last week I showed you rabbits' ears, right? So they send blood circulation to the ears, and that's when it comes close to the surface. And again, water can evaporate and bring the temperature down. Okay, so it's quite interesting that once water evaporates, it absorbs heat energy. And when water undergoes condensation from vapor to liquid, it's actually releases energy, releases heat. And I think that I showed you actually that, I think this is the first slide here, right? When water is liquid, right, the molecules stick together, but they don't form any particular structure. In ice, these bonds actually contribute to 3D structure, right? It's 3D, but the molecules in ice are farther away apart, right, than in the liquid. That surprisingly, being a solid, right, being a solid rather than liquid, ice can float. Yes? And this is the last part. So the last part is that water is solvent. What does mean solvent? Solvent means that you can mix a bunch of things with water. You can mix a lot of things with water. And a solution is a homogeneous. Homogeneous means even, right? Even mixture of substances. What usually helps to make solution more homogeneous is definitely heat, right? I'm sure you know that. Sugar in a hot water dissolves much faster, right, than in cold water. So solvent is what you mix with, dissolving. Basically, solvent is what you mix with. Solute is what you actually mix, right? So sugar is a solute while water is a solvent in the tea, right? Aqueous solution is when water is a solvent. But again, certain solutions are not necessarily aqueous. You can mix certain things with alcohol or again with some other stuff. But again, water is a solvent of life pretty much due only to the idea that it's a polar molecule, right? Polar molecule means uneven charges, right? Negative charge, positive charge. So this is salt, sodium chloride, right? So how you mix salt with the water? Easily, right? Chlorine ion will stick to their chlorine, which is negative, will stick to the positive hydrogens, right? And positive nitrogen will stick to the negative oxygen. Again, heat will facilitate because the movement of the molecules will be faster, right? So faster, which means these crystals will break apart, sodium to oxygen, chlorine to hydrogen, okay? And that's how actually things can get mixed. So when spheres of water molecules go around the ions, this is called a hydration shell, right? That's when molecules of water surround particular ion in the solution. Okay, and what is this? I'm not sure, but this is the same thing. Now, I really want you to pay attention to these definitions. You're probably familiar with them. Hydrophilic, the one that you can mix with the water. Whatever has charges will mix with the water. Hydrophobic will not mix with the water just because it doesn't have charges. What doesn't get mixed with the water?
Oil.
Oil, absolutely. Yes, so actually there are more hydrophilic. Hydro water, philic means actually love, right? So whatever love water, hydrophobic, whatever they don't like water. There's one more thing here that I want to add is amphiphilic. Amphiphilic is actually molecules that mix with both. A good example of amphiphilic, amphi means both, right? Soap. Like, you know, if you try to wash grease away from your hands with water, is it gonna work?
No.
Yeah, can you wash grease off your hands just with water?
No.
No.
What do you need? Do you need soap? How do you really like wash your hands, the grease off with soap? Okay, soap on one end can pick up grease. It will stick to grease. Another end of the soap molecule will stick to water, right? So which means that it's kind of like, what you can compare it to? I don't know. So basically soap will be able to stick to the grease and then let the water wash it away, okay? Because soap is amphiphilic. It can interact with both hydrophilic and hydrophobic molecules, okay? And concentration. So did you learn about concentration in your lab? Did your lab professor talk about concentrations?
I don't think so.
Yeah, I don't think so either.
No, not yet.
Oh yeah, okay. So concentration is basically like how much of substance you have in their solution, right? So think about rubbing alcohol. Do you remember what's the concentration of rubbing alcohol?
Um,
70%. Okay, 70% is the concentration of rubbing alcohol, right? Actually, whenever you like think about something else, what concentration of alcohol in beer?
20%?
20?
No, like 5 to
Where
10.
did you find such a strong beer? Tell me. I'd like to take it.
No, beer is a weak, right? I think it's below 10%, definitely below. What about tequila?
It's higher.
High.
Is that?
I think it's like 50%, right? I know tequila is higher than vodka for sure. So this is like basically example how much alcohol you mix with the water. That's the concentration, right? Usually, like saline. I'm sure you know what saline, right? This is their solution that people get for IV when they get dehydrated. Saline is 0.9% salt, sodium chloride, right? So that's the concentration, but there are other ways actually to figure out concentration is not by actual weight, like in grams, but by molecular mass, right? So usually there's something called 1 mole. 1 mole is this is called Avogadro number, 6.02 times 1023 molecules. This is just 1 unit, right? Of moles, right? Molarity is number of moles of solute per liter of solution. Let me explain to you what is that. You can, again, you can make a solution using concentration. Let's say, let me just write down here. Concentration, which is in grams, right? So you have 20% sugar solution. 20% sugar solution is 20 grams of sugar in 100 milliliters of water, right? So this is concentration. Molarity is about how many molecules of particular substance you have in solution. Because number of molecules is something crazy, so just to make a shortcut, you say mole. Okay, mole is this amount of molecules, right? So with the moles, you take, let's say, do you have an example here? For the moles, you take, let's say, the same sodium chlorine, right? In the sodium chlorine, you take, did I close this? I think I closed it. Just give me a second. Sorry. Just need the periodic table again. Okay, so sodium is 11, right? Chlorine is 17. So 28, basically, right? So, no, that's not right. That's not right. I don't have a number. Basically, you take atomic weight of chlorine and you take atomic weight of sodium, right? You combine them together, and this is a mole, 1 mole. Just don't remember what's atomic weight of both of them. I think it's not that relevant right now. Sorry. Do I have it here? See the weight. Okay, I think sodium is 21. In chlorine, atomic weight is 36. So I combine chlorine and, chlorine and sodium, atomic weight, right? And for 100 cc of water, that will be the mole. Okay, so let's say hypothetically it's 48, let's say 48, 1 m or mole of salt, right? So I take 48 and I put in 100 milliliters of water. This is solution by molarity, not by weight, not by grams, but by molarity. If I want to prepare 2 mole solution, I just double this number, right? 3 mole, I triple this number. I'm not sure if we're gonna get back to this, but I don't think it's that important in these days, what is mole, but it's again, it's a slightly different approach how to prepare solutions rather than by weight. And possible evolution of life on other planets, and people still hope that there will be life somewhere else in space. Do you believe there's life on other planets? Guys, do you believe there's life on other planets?
Yes.
Maybe.
Okay, Mighty, why do you believe there is life on other planets?
I just feel like there has to be something beyond us. Like if we were able to make life on Earth, or like, you know, evolve into what we are today, I feel like in other planets that could be possible, because there has been evidence of life found on other planets too. So it's like it might not be as advanced as humans, but you know, there has to be life on other planets.
Okay, Will, what do you think there is no life on other planets?
I just think we would have found it by now if it was out there.
Yeah. Other ideas? Who else want to say something? Brianna, what do you think?
I think yes, because there's like water on Mars and stuff like that. So
there was water.
There was, yeah. So I feel like there's probably other planets that we haven't discovered yet that have life.
Okay, yeah. Gabriel, what about you?
I don't know. I think maybe. Sometimes I read, think here and there, but maybe.
Yeah, that's yeah, maybe like I have other problems right now to think about than life on other planets. I mean, like, if there's something we have to face and handle, that's gonna be a different story, right? But when it's like hypothetically, I think it doesn't really affect us much. So yeah, but possibly. Okay, anyways, you said there's no life without water. I can challenge that too. Who knows? Maybe there's life without water. Actually, it's just a different form. Okay, so the last part is about acids and bases. Okay, so you see, this is the thing. Water, right? Can the molecule itself break apart? Yeah, it can, but it's there are a bunch of other chemicals that can give off hydrogen electron, right? So anyways, concentration of hydrogen electrons in solution pretty much determines solution acidity, alkalinity, or whether solution is neutral or not, right? If water molecule loses this hydrogen, right, it turns into something called hydroxide ion, right? This is OH negative. This is hydroxide ion. It's a very, very important ion as well. Hydrogen ion is super important. This is not important iron. If this water molecule picks up additional hydrogen, it might happen. It turns to hydronium ion, but it's usually hydronium ion is the same as water plus hydrogen ion. So the thing is, let me just write it on the whiteboard and it'll make more sense. Okay. Now, water molecule doesn't really tend, it seriously doesn't tend much to break down into hydrogen and hydroxide ions, right? It doesn't. But if you see hypothetically like this is the water, right? It's the water, you have bunch of hydrogen ions, bunch of hydroxyl ions. If they imbalance, really imbalance, how did I leave my phone? Oh, awesome. But if they balanced, the amount of hydrogen ions and hydroxyl ions is the same, this solution is called neutral. What is really neutral is distilled water. You know what's distilled water? You take water, boil it, right? And collect vapor. And vapor undergoes condensation, turns into liquid. This is distilled water, means you don't have anything mixed with this water. Okay, no other chemicals. If in solution, you mix something with water and concentration of hydrogen ions goes up, this is called an acid. If you mix something with water that gives extra hydroxyl ions and less hydrogen ions, more hydroxyl, this is the base. It's sometimes called alkalinic solution. Why it's relevant? It is really relevant because actually all this concept of acids and bases plays huge role in biology. Okay, so what you can see, acid is substance that increases concentration of solution. You know what is this, you know what is this? HCl. This is hydrochloric acid. This is acid that is present in your stomach, right? It helps you to digest proteins. Hydrochloric acid really tends to break down into hydrogen ion and chlorine ions. So if you mix water with hydrochloric acid, what are you gonna get? You're gonna get an acid, right? Because you're gonna increase concentration of hydrogen ions. This is when you have less hydrogen ions, but more hydroxyl ions. There are strong acids, there are weak acids, weak bases, strong bases, right? But as I said, when this is balanced, this is neutral, right? Salts are neutral. Like you take sodium chloride, right? It's a salt. It doesn't have hydrogen or hydroxyl ions. It's not going to affect acidity of the water, acidity or alkalinity, okay? Now, to measure whether acid or base, strong or weak, there is what's called a pH scale, right? Don't really worry about the logs, whatever. Don't worry. What really matters, let's see. What really matters is that it goes from 0 to 14. From 0 to 7 acids, 7 is neutral, right? Now, 6.99 will be slightly acidic. 7.01 will be already slightly alkalinic. So neutral is just 7. From 7 to 14, these are bases. What are acids? Acids usually sour, right? Like citric acid found in lemons, right? Acids usually burn, strong acids, I mean. Like remember formic acid released by ants, right? Acids usually corrode metals, right? Like acidic rains destroy metal in the cars, right? Yeah, they corrode them. So very strong acid is, you don't see it here, sulfuric acid. Have you heard about sulfuric acid? Yeah, I mean like drop of acid can just like make a severe burn, right? Hydrochloric acid is quite strong acid, right? Gastric juice and stomach. Vinegar, wines, all sodas are acidic. Black coffee is acidic. Urine is acidic. Saliva is acidic.
Human blood, slightly alkalinic, slightly. Tears, the same, right? Seawater, and inside small intestine is alkalinic actually. Milk of magnesia, ammonia, bleach, oven cleaners, actually all household cleaning items, they are alkalinic, okay? So as I said, you see, if only water is neutral, so it plays really a huge role. All the fluids, right? Body fluids in living organisms, really important role whether they acid or bases. Now, so again, keep in mind, pH from 0 to 7, acid. pH from 7 to 14 is base, yeah? The lower the number, the stronger the acid. The higher the number, strong base, right? So whatever's around neutral is weak, on extreme is strong. Okay, guys?
Okay.
Now, the thing is that we're not going to talk about that. This is the last part. This is the last slide I'm talking about, just to cheer you up a little bit. Buffers. The thing is that you really have to keep, I'm talking about human body, for example. You really have to keep certain fluids stable in terms of pH. So pH can fluctuate, but it shouldn't fluctuate much, right? As I said, your blood is slightly alkalinic. If blood becomes acidic, you can pass out. If it becomes too alkalinic, you'll pass out as well. So there are systems that maintain pH within normal range. This system is called buffers, okay? So what buffers do are substances that can actually either contribute hydrogen to make solution less alkalinic, right? Or they can pick up hydrogen to make solution less acidic, right? And what they do, these buffers, they convert strong acid to weak acids and strong bases to weak bases. Let me just give you example, just one example, and we'll be done. Okay. What did I do? Oh my gosh, sorry. This is, who knows what's this acid? Anyone knows this name of this acid? This is carbonic acid. Carbonic acid you can get H2O plus CO2 gives you carbonic acid, okay? Water plus carbon dioxide, this is carbonic acid. Now, another thing that carbonic acid can do it can break down into hydrogen ion and bicarbonate ion. This is bicarbonate ion, right? So this is a hydrogen ion. Now, if you have bicarbonate ion circulating, right, it can easily pick up hydrogen, sorry. It can easily pick up hydrogen. And turn into carbonic acid. Carbonic acid is a weak acid. So basically, what cells usually do, cells usually get rid of hydrogen ion, keep this one, right? They keep this one because if their acidity goes up, it can always easily bind this hydrogen and reduce acidity by forming carbonic acid, okay? So this is a major buffer actually in, it's a major buffer in living organisms, the carbonic acid buffer, because it can contribute hydrogen ion, it can pick up hydrogen ion, right? Regulating the concentration, regulating pH, okay?
I'm not sure if we're gonna get back to this buffer system. Maybe. I know I usually teach the buffer systems in anatomy class when we talk about the pH regulation. But this is just to give you like an example how it can work, right? Whenever you can neutralize this, you reduce acidity. Whenever you can release this, you increase acidity. Okay. Questions? You are such a quiet class. Oh my gosh, from all classes this semester, you are the most quiet. Okay, you can think about questions when I take the attendance. Okay, Iman, present here?
Yeah, I'm here.
Okay, you know what? I'll share this with you so you're gonna see what I'm doing. Okay, Matey, yes, present?
Present.
Okay, Roshana, I saw you. Aja?
Here. Here.
Naila? Yes? Okay, number
Here.
6 here? Okay, Natis? Yes? Here?
Matisse, and yes, I'm here.
Okay. Johnny?
Here.
Okay, Kevin?
I'm here.
Okay. Juliana?
Here.
Okay, Brianna is here, I saw her. Shalom, I saw. Jamarius, I saw. Soraya? Yes? No?
Here.
Here?
Hello? Yeah.
Ophelia? Ophelia? Okay, Joseph? Okay, Gabriel is here. William is here. Azra is here. Olivia? Yes? Macarena?
I'm here.
Mirandi?
Here.
Tiffany? Tiffany? Tiffany. Okay, Tahmina.
Here.
Okay, Yvonne, I think she's here. Dominic is here. Leonardo is here. Ebony? Ebony. Ebony. Okay. Okay, guys, so listen. I'll definitely post I mean, over this weekend, the beginning of next week, I will post information about the quiz. But as I said, just think that next Thursday from 8 to 8:40, you will have 30 minutes limit to take a quiz, 20 questions, either multiple choice or true false, okay? So we're gonna meet at 8:30, oh sorry, 8:40. We'll meet for the class, okay? So 2 chapters for the quiz, chapter 2, chapter 3. And you also have to complete exercises from their Mastering Biology. So whatever is posted there for you. Okay. Okay, guys. Then I'll see you next Thursday if you don't have questions. Okay. But with anything, just email me.
Okay.
Thank you.
So bye.
Yeah.
Enjoy your long weekend.
You too.
Bye. Thank you.
Bye, guys. Bye. О, привет.
Ты здесь?
Да, я только закончила класс. Да. Вот только класс закончила. Прям вовремя. Ну, как дела? Что-то такая смурная. Да. Что с утра уже смурная? Что, говорю, с утра уже смурная? Заходи.
Давай, я тебя жду, поднимайся.
Нет, пускай я поднимусь потом. Привет. Нет, Ариэля, я уже закончила. Сейчас я переоденусь, мы с тобой съездим. Я тебе бамбу. Хочешь? Потом домой. Альмок придет вечером. Азик еще не вставал? Переоденусь. Мы с тобой сейчас съездим за бамбу. Потом я вернусь. Сделаем математику, почитаем. Гуляем, может быть. Или workout надо будет сделать.
А Лазарда звали Эрик Лазар. А Эрик, это как его звали?
Eric Lazard?
Да. Там кто Эрик Лазар.
Lazard, это их начальник был.
Почему Лазарь такая? Лазар.
Похож на Lazard. Да?
Да. Он был Лазар очень.
Окей, пошли съездим сейчас в магазин.
Мама, а почему из Хэллоуин?
А ты знаешь, что Альмок с тобой тоже?
А почему Хэллоуин? Thomas father-in-law.
Привет. Привет. Да. Что, кстати? Встал? Да. Ну, час назад.
Да. Ну слушай, Гань, ну я откуда знаю, ну непонятно. Сказали, позвонят. Я не могу там сильно налегать. Как ты на людей налегать? Это мой начальник.
О, спасибо. Нет. А что?
Напишу тогда насчет себе стукать.
Окей.
А я скажу?
Ты куда?
Да, идем. Бери свой скутер, кофе. Чего? Кому? Ладно. Пошли.
Знаешь, почему they call on the giant, one giant? Ань, как ты пойдешь? Как ты пойдешь? Ради, как ты пойдешь? Ради, кого? А что сентябрь 25? Я не знаю. Знаешь, что этот never не надо очень. Я хочу это. Мое яйцо. О, там surprising. Дай мне тарелочку. Там surprising. Нам совсем что делать? А вот там что? Ой. О! Смотри, как она. Она может ехать сам. Смотри. Хорошенькая машинка такая. Смотри на это. Алло? Мама, сейчас, да. Короче, что-нибудь.
Ты можешь принести снизу?
Да?
Можешь принести снизу вот этот subtraction, которая в бейсменте осталась? Принеси, ты вчера в бейсменте сделал subtraction.
А, ты, а если... Ой, извини, ты запутала. Что ты с этим?
Нет.
В порядке?
Да. Just, I don't know. It just doesn't feel like I'm going anywhere. Also, much as I like hanging out with friends, I really want like a partner.
Girlfriend.
Just not in any shape. Not a shape. Sad.
А вот это какой?
Это можно закончить. Давай смотри.
Какой? Сколько? Сколько? Мало.
Сделаем это. Смотри. Subtract your way through the maze to get the turtle to the sea. Вот смотри. 6 minus 6, 0. Okay. Then 7 minus 3, 4. Вот это maze.
Это?
Вот это 4 странички. Да? Хорошо.
Хорошо.
Начнем с этого.
Раз,
Тебе
два.
веселее. Раз, два.
Как мы вот это?
Вот это нужно subtract each number from the center number of the sheet and write the answers in the outside ring. So 7 minus 3 is 4. 7 minus 7 is 0. 7 minus 2, 7 minus 5, 7 minus 3.
У нас еще не будет прицела.
Сейчас я напишу. Слушай, ну надо еще. Что он может делать? Он сказал, что точно все будет как делать.
Я обещал.
Ну еще.
Вот. Смотри, как я это. А сейчас что делать? А сейчас
Ариль, ты сделал плюс здесь. Ты все сделал плюсы. Ариль, это все майнус. Фу. Ариль, посмотри сюда. Это майнус, это не плюс. Исправь, пожалуйста.
А что там я сделала? Кисер-кукер-кисер. Eraser.
Сейчас очень история будет весело.
Что?
Black man died after being restrained by Rochester police.
Oh no. And Ariel's in Rochester. Oh no.
Кто дай? А что там было написано?
You know, Trump wants to cut funding to cities, which is correct. I mean, listen, they're not listening at all. I think once you start cutting money, that's when they're going to start listening. Because these democratic cities, these democratic mayors are doing nothing. Absolutely nothing. Like Portland, jeez, that's horrible. In New York City, oh my god.
Так что было в марте.
Да.
Да. Сейчас оно вышло видео.
And take a look at this. It's a good example. Yeah, and my folks just looked at 2 weeks ago.
Мама, когда вот это звук мама. Я знаю, что я закончу. Я сейчас еще не закончила.
Сейчас.
Microsoft.
Закончил.
Все?
Мама, когда вот это... Я знаю, что я закончил.
Окей, а теперь сделаем мейс. На, сделай мейс. Молодец.
Молодец.
А вот это, когда я включу, это значит, что я закончила.
Там мейс.
You don't even see this at all in the media. Maybe a few news outlets, like a few, but if they actually show this to people, there's gonna be like big opposition.
Мама, вот это правильно вот так делать? Делать line.
Да, ты делаешь line, правильно, смотри. Ты, you find the right answer, right? 7 minus 5, сколько будет? 7 minus 5, сколько? 2 или 3? 7 minus 5, сколько? Нет. Скажи мне, сколько будет 7 minus 5? 2. 2. Next one, 6 minus 6. 1 or 0?
0.
0. The next one, 7 minus 3. 3 or 4?
4.
4. What the project?
Oh.
Давай.
This is like which street? Everyone's
А сейчас... самое супер.
Да. Что? Что происходит? Значит, это сейчас происходит?
Нет,
Это было?
это, смотри, это было в March 23. Теперь они released footage, как полиция установила. Ну вот. И теперь это released, и они могут...
Finish.
Вышел из медиа?
Да, я вышла оттуда. Я на finish.
На finish. Вау, какой молодец. Ой, умничка. Умничка. Окей, теперь вот это.
Что вот это? Что это?
А вот это, смотри, ты делаешь, смотри. На каждый листочек ты должен написать число. 7 minus 3 на этом листочке. 7 minus 4 пишешь 3. 7 minus 6 сколько будет?
Minus 6 будет... Ну что 7 minus
6 будет?
minus 4.
7 minus 6 будет? 13. Какой 13?
7.
7 minus 6 сколько будет? Что это? 1. Ты здесь пишешь 1. 7 minus 3 ты пишешь 4. А, вот это сделали. Все. Ну, почитаем, а потом выясним.
Чего тут будет?
Я буду workout, это буду сам делать.
А мы что делаем?
Сейчас ты released.
Они там сейчас вывести.
Wow.
This is good. This is good.
Привет. Хорошо, хорошо. Угу. Хорошо. Угу. Угу. Черная рубашка есть, а штаны надо посмотреть. Могу купить, в принципе. Ну. Угу. Хорошо. 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 Да, пожалуйста. Угу. Да. Увидимся. Пока. Ваше ожидание. Что indoor dining открывается.
What's got indoor dining?
So, это будет, I think, up to 25 people inside. That's more, what I like about this, so it's indoor. I think I'm gonna have to wear a mask now forever. No. The thing is, so when you go outside, you have to bring the food through the door and then around the whole place. The chance of dropping it is like higher, obviously. No, if there's indoor, I could just take the food right from the kitchen and give it to the person because it's inside, so it's easier. And then communication is faster, so the only thing is, он сказал, что не надо черную рубашку, не надо черные штаны. Yeah. Хорошо.
Может, тебе черные джинсы?
Да.
Давай снизу.
Джинсенина, like черные просто. This is good. This is good. This actually made me like happier now.
Мама, почему надо быть, почему сладкое, а не вежливое?
Что? Что ты болтаешь, а? Какие сваты вежливые, а? Какие сваты вежливые?
Некоторые сваты невежливые, да? Да?
Ты не такой сладкий.
Может, я вылизу твой нос?
Нет.
А если я буду это чушь?
Фигу. Не знаю. Нет, нет, стоп.
А что если увижу, у тебя слюни на попе?
Фу. Фу. Так, мои руки. И мои руки. Да, все, завтра открывается индор.
Ну, покажи мне. Ты сделал рейд? Куда ты пошел?
А мои руки?
О, more news, кстати. Помнишь, эта девочка, которая на флейте со мной играла? Right? Allie? She saw my Fiddler on the Roof video. It was on YouTube, and she said it's really pretty and beautiful. And
А
she's like,
стриках уже вместо моих слюни в стриках, а не вместо моих.
Рио, с вами разговариваю.
Закончи, пожалуйста, надо почитать.
And she wants me to make an arrangement for piano. Все сделаю.
Ари, ты закончил? Перестань кидать.
Абракадабра!
Ари, ты закончил?
I could do some cool like counterpart in the piano.
And it's good that you keep on
Huh? No, не обещала, да? Lila is a good news. Just to get cats are just cute. Ну давай. Why not go to Israel? There are a bunch of stray cats.
Мама, там холод.
No. I think it depends on how you approach them. What if some cats are simply like, they're actually friendly, but their past owner like abused them? And then when they meet someone new who really wants to be friendly with, they open up and warm up to them.
But I'm talking about kitten. But take a street kitten.
Мама, смотри, что случилось.
Что ты потом сделал? Молодец. Ари, давай ты уже закончишь. Пожалуйста.
Бракия. Эмендо.
Yeah, he actually got an apartment in New York City. Which I actually saw on Snapchat, which is like where I see a bunch of the birthday kids. A lot of them, they got apartments in Boston.
So you went to Boston?
No, I really don't know what's the point of getting an apartment if you're gonna do online school. I mean, what I do understand is probably to get out of like the home and just have more independence. In terms of just financing, if I were a year older, then maybe I would do that. But also, it's just, I don't think it's a good financial move. You're paying for school, that's probably a few $1,000 cheaper,
Mama,
but
я
it's
не
still
могу закончить. Мама, даже не могу закончить.
Чего ты не можешь закончить, а?
Это.
Давай, принеси сюда.
Да.
Принеси сюда. Положи эту палку, принеси сюда.
Посмотри на это.
Что это такое? Ты мне скажешь, что это такое? Что сделал?
Это я случайно.
Не случайно. 7 minus 6.
Мам, смотри.
Ты не закончил? Так закончи, Алиев. Пожалуйста. Закончи. Six minus 1. No. 6 minus 0. 7 minus 0. 7 minus 6. 1. 7 minus 3. 7 minus 5. 7 minus 2. 7 minus 5, 2. So 7 minus 2. Okay, 7 is 7 minus 5. 7 minus 2 is 5. 7 minus 4 is 3. Yeah. Okay. 7 minus 7. 5 minus 0. 5 minus 1. 1. 5 minus 4. So 5 minus 1 is 4. 5 minus 4 будет. 5 minus 1 is 4. So 5 minus 4 будет 2. 5 minus 1 is 4. 5 minus 4 is 1.
Yay! Easier.
Okay, this time. 5 minus 2 is 4. 5 minus 2 сколько будет? 3. Значит, 5 minus 3 будет сколько? 5 minus 2 is 3. 5 minus 3 будет... So 5 minus 2 is 3. 5 minus 3 будет сколько?
Я подумай, come on, подумай.
Не подумай, если 5 plus 2 plus 3 будет 5. Значит, 5 minus 3 будет сколько? 2. And 5 minus 5 будет 6 minus 1. 5. 6 minus 0. 6 minus 5. 6 minus 1 is 5, which 6 minus 5 is 4. And у тебя you have 3 numbers. Послушай сюда, смотри. Дай сюда, дай сюда, дай сюда. Не надо считать. Смотри, дайте покажу. 6, 5 plus 1 equals 6, which means if 6 minus 1 equals 5, значит 6 minus 5 equals 1.
You have three numbers, they all related. Okay, 6 minus 4, which is 6 minus 4 is
3.
No.
2.
2. Sure. 6 minus 4 is 2. Which is 6 minus 2, which is 4. Again, 6 minus 4 is 2. Значит, 6 minus 2 будет сколько? Ты можешь сюда смотреть? No, you have three numbers, 4, 2, and 6. Okay, they all related, these numbers. This is 6 minus 4 is 2, which 6 minus 2 будет 4. Молодец.
А ну посмотри на это.
Ну, сама можешь. Okay, and 6 minus 3 будет 6 minus 3 будет double. 3. Окей, сюда смотри. 4 minus 0 сколько? 4 minus 0 сколько?
А я это скажу.
4 minus 1 будет сколько? Сюда смотри. Нет, 4 minus 1 сколько будет? 3. 3. And 4 minus 3 сколько будет?
9.
4 minus 3. So 4 minus 1 is 3. 4 minus 3 будет 4. Считай, сколько будет 4 minus 3. Считай.
What?
4 minus 3 будет сколько? Сколько будет 4 minus 3?
2.
And 4 minus 4?
0.
And 4 minus 1?
3. Что?
Таки можешь со мной сколько заниматься?
Не, я сейчас смою.
Хорошо, смой.
А вы кладу свой один.
Давай, смывай.
Как это смывать?
Мылом и водой. Почему начнешь? Как так можно? You like watch the city that you are the maid. You destroy it and you do nothing.
Yeah.
And then like when you basically have to face the consequences, you start like pointing fingers and blaming a bunch of people, especially Trump. And then Trump is responsible for that.
Yeah. trunk has a lot of gray brick.
That's wonderful.
A lot of cuts.
Very
Oh yeah, left ball. Literally, as soon as he started funding, like de Blasio, like, you didn't help us, and now you wanted to fund us. You didn't help the city at all.
Молодец. Так, я пойду в Вы же начали что новое?
Нет, еще. Я как лайла. Молодец.
Never named you. I've been named you. I know what to understand. Следующий голову, следующий меня. I